Hi everyone, and welcome to the section on reaction rates. In the past, we've known about reactions as being something changing from one thing to another. So the important thing about when a chemical reaction is taking place is we're actually having a look at something changing the type of material it is. So if it doesn't change the type of material it is simply changing states, and we're talking about states of matter here. So the three states of matter we know about are gases, liquids, and solids. If something's in its gaseous form, it's had a lot more energy. So the energy required to go to a gas is increasing. So as we go across, we've got increasing energy required. But really what that's talking about, and we're going to draw these particles here as single dots, but if we talk about these single dots, the more energy we give it, the further apart the molecules are, and the less the secondary interactions hold them closely together. So in a solid, the secondary interactions are holding the molecules closer, and therefore we get a more rigid structure. Now, when we're talking about chemical reactions, this isn't what we're talking about at all. We're talking about these two molecules colliding and forming something else. So it tends to be two different things that collide and form something else. And to do that, they have to have enough energy for the collision to be successful, and it has to be in the right orientation. So the bigger the molecule, the more important or the harder it is for a reaction to occur, because there's only a tiny bit that can be that is the right orientation, whereas smaller molecules tend to have easier reactions. So let's take a look at one. Okay, so here we have a reaction simulator. So if we have a look here, we've got these two types of molecules, A and B. So we've got this molecule here, A. B, C is a different type of molecule, and then we're getting these two different ones formed. So let's have a look at how that looks. So we can see that as they collide, we're getting different things forming. But you can see that time we didn't actually get the formation because it didn't hit in the right way. So sometimes they're going to collide and not actually cause the change because they haven't hit in the right orientation, and we can see that happening here. Alright, so let's increase the number of molecules. So same reaction, but this time we're going to increase the amount that there are. So let's make that happen. Alright, so we've got lots of A's, and that's all we've got at the moment. So we've only got A's in there. So we can see the A's are colliding together with some sort of energy, and we can lower that energy here. So we're going to cool it right down. So lowering that temperature right down. We can see all that's happened now is that they're moving slower. So we've got these slowly moving particles. We can raise the temperature and we'll get them moving faster. And that's great. We've got these fast moving molecules, but because we've only got molecules A in there, we're not getting anything else form. So we've just got A molecules colliding. So they're more likely to be in a gas state here. So let's lower that back down again. And I don't know if you're noticing what's going on over here in this graph. We'll talk about what this graph means in a minute. So let's add some BC molecules. Okay, so we've got some BC molecules in here now. Right, so they're hitting, but can we see that in this reaction, although they're hitting each other, nothing new is forming. So that means that they don't have enough energy to have the new molecules forming. So let's go and have a look at what this graph's telling us. This is the energy that we are starting with. So this green line tells us how much energy is in the reaction vessel. So if we have a look at this graph, we can see that it has this bump that it has to get over. So this part here, we can see there's a blue line underneath here. That tells us where the reaction is starting. So that's about where we're starting. And then this here tells us that how much energy we're going to finish with. So if we take a look at this, we've got to get over this bump to get to our products. So this is our reactants here. We've got a bump to get over to get to our products. That's called the energy of activation. So that's the energy required to have successful collisions. So let's raise the energy to that energy of activation. So still we're at where the product should the product energy is just about, so let's raise a little bit more. Okay, so that's our product energy. We can see that we're getting increased number of collisions, so they're hitting each other more frequently, but still not with enough energy. So let's raise it a little bit higher to that bump now. Nearly. Okay, we've passed the energy of activation. So now as they hit each other, if we hit in the right orientation, we should be able to form this AB. So we can see now we're getting some AB formed because it's hitting the right orientation. Alright, so if we think about what else we could do, so we've increased the temperature and that's increased the number of collisions or frequency of collisions. We could also increase the frequency of collisions by increasing the concentration. So let's increase the concentration of this B. So I'm adding more B in there. Alright, so we are now having more and more collisions. And I'm also going to increase the amount of A. So you can see now we're having a lot more collisions, and the amount of the product, so the amount of the yellow and the purple combining, is greater. So we're getting more successful collisions to form that AB.